Good afternoon, everyone in virtual space. My name is David John Gagne. I'm the head of the Analytics and Integrated Machine Learning Group. Welcome to the CVP Visitor Program Seminar Series. Today's speaker is Ver Hoef. He is a mathematics PhD student at Colorado State University and has been visiting here for the past summer. His research interests include things like geometric deep learning, topological data analysis, and applied harmonic analysis. Interesting fact about Landers: before graduate school, he was an officer on a NOAA hydrographic research ship, doing both ship handling and operations, as well as collecting and processing hydrographic data. So then he went off into mathematics. Landers now come back into more real-world applications with his collaborations not only on this project with rotationally invariant CNNs, but also with using topological data analysis on, I believe it's on satellite data.
Yep.
So today his presentation will be on comparing rotationally invariant CNNs with classical CNNs when predicting storm mode. One quick, for anyone watching, if you can send a test message in the Slido to make sure it's working. If someone could send one just to make sure we have good audio. We're good? The citation's nodding, so I'll turn it over to Lander. Thank you.
Thank you, DJ, and thank you for inviting me to come and be a visitor here. It's been an absolute pleasure. I've had a great and hopefully relatively productive summer, so yeah. Yes, so this is okay. I'm somewhat echoey and feedbacky. Do I need to just move? Okay, we're good now. Okay. Yes. So I'm talking today about work we did this summer on looking at rotationally invariant CNNs on storm modes. So first, let's talk about the overall problem that sort of motivated all of this, and that is looking at forecast data, and there are existing algorithms that can identify when there is a storm based on certain criteria and can sort of pick that out. But a further question is, what type of storm is this? Is this sort of a disorganized broad storm? Is it a squall line or a quasi-linear system? Or is it a very intense supercell? And that's an interesting question to try and provide to forecasters, because that can inform forecasts about severe weather events and ongoing weather occurrences of having this information about what type of storm we're dealing with. So the AIML group here has built up an existing algorithm to do this process using both dense neural networks and convolutional neural networks. But what I was interested in is whether we can look at how this process might be modified and potentially improved. That remains an open question. Using this new field of sort of computer learning merged with mathematics called geometric deep learning. So the idea of geometric deep learning is we want to exploit symmetries of our input space. So what I mean by symmetries is just any transformation of this space that after you apply the transformation, you more or less get the original space back. So here are some symmetries of a cube, where in B and C we see we've rotated this around one of our faces by 90 degrees, where we get the original cube back. In D, we've flipped it over. Again, we get the original thing back. E here is an example of a non-symmetry, where we're rotating around one of the faces, but we haven't rotated by a fixed 90 degrees, so the output is, in some sense, different than our original input. So we want to try and identify useful symmetries of our input space and build an architecture that can utilize them to get better results, is the sort of overall goal of geometric deep learning. And the core tool to be able to do this is convolution. So classical, this is discrete convolution. This has been a mainstay of machine learning for a number of years now. Let's talk about how it works real quick. So the overall formula is up here in the upper left-hand corner, and the point of this is that our output is a new function, this convolution function x star theta, where x here is a signal or an image, most typically. So that would be this grayscale image of an upside down triangle. And theta is our filter. This is the thing that we are sort of using to interpret our image. And in this example, that's this little red box, where in this case, that's a 3x3 box, which we can think of as being 0, except with 1s on the vertical center vertical line here. And in convolution, we take this filter and translate it all around the input image, and for each translation, multiply it against the base image, and then add up everything that we get. So we can see in this upper right-hand corner, at this position for the filter, there's only one pixel of overlap between non-zero places where the background image is non-zero and where the filter is non-zero. And so we get an output of a 1, which shows up in the pixel over on the right that there's the arrow pointing to, because that's the location corresponding to where this box is. And in the lower right, we can see there's 2 pixels of overlap. So in the location corresponding to that box over on the right, we have a pixel with a value of 2 from having added all of this up. And the lower left, we can see this process of shifting this box, this filter, all around our image, translating it all around, and the resulting outputs in the pixels on the right. And with this particular filter, what we can see is that this gives us sort of a vertical smearing. Our triangle gets smeared out a little bit in the vertical direction. But with different filters, this is going to have different effects. And the filter here is, in most machine learning applications, what is actually learned. This is the thing that can change and morph to give you different information about your filter, about your base image. Now, one of the interesting and powerful properties of convolution is that it is translationally equivariant. So what does that mean? That means that if I apply a translation to my original image, like for instance, shifting it down a little bit, then applying that translation and then performing a convolution is the same thing as applying a convolution to the original image and then applying the translation. So in other words, I can either think about going from the top left to the bottom left over to the bottom right, is the same as going from the top left to the top right and then down to the bottom right. Those give me the same answer. And so we can think about this as convolution respects translation. It plays nice with it. And that is one of the attributes of convolution that has made it such a powerful machine learning algorithm. What about rotation? It would be lovely if it played well with rotation as well, but unfortunately it doesn't. as we can see here, if I take my triangle here and rotate it, the output of the convolution is very different. Instead of having everything be sort of smeared and about the same intensity, in this case, the vertical line, because it's sort of in line with the non-zero part of the filter, doesn't get opened up and smeared, it just gets extremely intense. These are values of 3 all along the vertical, where in the original convolution we didn't ever get anything more than a 2. So what we're going to try and do is modify, and what has in fact already been done by others for a while, is to modify convolution to not only respect translation, but also respect rotation. And the tool to do this is called group convolution. So classical convolution is up in the top here, that's what we've seen before. And group convolution is down in the bottom. It looks very similar, where really the change is we've replaced this T, a location on the grid where we sort of translated our filter to, by a group element H, where here I mean group in the sense of algebra, algebraic groups and group theory, which for those who are not deep into algebra, we can think of this as being the set of symmetries of the space. So here we're applying some symmetrical transformation rather than just a translation. And one of the things that's interesting and important to note here is that this new convolution, group convolution, is a function on this group. So rather than being a function on just a grid or the plane, now for any symmetry I have an output, which in some groups would be very hard to visualize. Luckily for us, we can think of this as being sort of split, because the groups we're going to be interested in are rotations of the plane and translations. And translations, we already know how to visualize those. We can visualize those as being on a grid. And then we can think about that as being a separate grid for each type of rotation that we have. So we can think about rotating our filter and then having a whole grid associated with that rotated filter, which is what we see here. We have our triangle and the sort of vertically smeared version that we get when we apply our original filter. And we also have the version where if we rotate our filter, that is very much equivalent to sort of rotating our original image and using the original filter. We can sort of interchange those very nicely. And we keep track of how we rotated the filter, and then we're able to rotate the outputted convolution back so that everything stays lined up nicely. We'll look more at that in a second. But the advantage of this now is if I rotate my original image, all I have done is permute the outputs. So now rotation of our input becomes permutation of these slices of output, which output corresponds to which rotation. And this is a very well-behaved and sort of respectful operation and rotation. So we have achieved this rotational equivariance. We can think of, well, it's not quite as simple as the translational equivariance of a conventional CNN, where translating something simply moves it in the output, but it is equally as nice and predictable for machine learning applications. One final note before we move on is we do technically have a third type of convolution here, where in a convolutional neural network, we're going to want to take these convolutions and apply them one after another, and use the output of one convolution as the input to the next. And as we said before, the output of this group convolution is not a function on the grid, but is now a function on this group. And so in this final convolution, this is the same group convolution, except that our signal, x, our image, and our filter, theta, are now functions from the group to the real numbers rather than from the grid. And that means that this, the action of the symmetry is going to be somewhat different. The action of h on the filter here is different than when it is acting on just the grid. Okay, so in a more general setting, now moving away from this sort of very simple triangle with the little vertical line, now we have the case we're in where we have our translations, and our symmetries also include now 4 rotations by 90 degrees, because those are the nice rotations of a square. And we can see here too that when we rotate the filter, we're actually rotating the filter not around the center of itself, but around the center of the image, because we want this correspondence, this equivalence between rotating the filter and rotating the image, and rotating around the center of the image is sort of the only center that makes sense for image data. And that's why in this figure we see that the filter is showing up it's sort of starting in different corners of the image based on that rotation. And then when we stack them all up in after applying them here, we want to stack them all up so that the filter's starting positions line up. So that way they are consistent moving forward. And then in future steps, this new group convolution, we can think of no longer as having sort of all of these distinct filters, but a single filter that is now just moving throughout this group structure. Now, you might have noticed that in the title of this and the title of the talk and the title of this slide, I'm talking about rotational invariance, where before I've talked about equivariance. So this convolution gives us equivariance. We're rotating the input is going to shuffle around these slices in the output. To move from that to invariance, where the output just simply does not change when we rotate our input, all we need to do is apply some sort of transformation that can collapse this stack down in a way that doesn't depend on the ordering. You could take the pixel-wise average, or you could take the pixel-wise maximum, or any of a number of more complicated operations that don't depend on the ordering of these slices. So, how can we put this into an architecture? So we'll start with a classical CNN architecture. We start with classical convolution. Let's start with the classical architecture, where we start with an input image. We have some number of filters. Rather than dealing with just a single filter, we want to extract many different attributes from this image, and so we want a number of different filters. Apply the convolution, and each of these outputs are stored as these feature activations, these parallelograms in this figure. We want to apply nonlinearity, so we do activation functions. We want to look at different scales, so we apply pooling. And then we do it all again, where in future steps, these filters are able to pull information from the whole, each filter is able to pull information from all of the feature activations in the previous step and consolidate that into new encoded information, which gets encoded and pooled and repeated until we're satisfied and that this has been sort of encoded well enough. At that point, we can flatten our remaining feature activations, which are in this still sort of grids, into a long vector, which then we can feed into a conventional dense neural network or a multi-layer perceptron down to our final outputs. Okay, so what happens when we want to make this rotationally invariant? Well, this is effectively the same picture with some modifications. We start again with our input. We again have some number of filters, but now we take these filters and rotate them 4 ways and take the resulting outputs and put them into these stacks that we showed before, these stacks of 4 slices of traditional convolutions, which together represent a single feature activation, but over a group rather than over just a grid. And we do activation functions, we do pooling, and we repeat. And again, our future filters are able to pull from across all the same corresponding positions in all of these feature activations, where here the corresponding position also includes which of these 4 slices we are currently living on. Again, we do this until we are happy, and then before we can flatten here, we have one additional step, which is this rotationally invariant pooling, where we move from equivariance, which we have had through all of these convolutional layers, to invariance. We collapse these stacks of 4 slices down into a single slice that is now rotationally invariant. And from here on out, everything is exactly the same as in the conventional CNN, just with rotational invariance added. Cool. So what can we do with this? So the first thing we did was we tested this on a synthetic data set, which was generated. We took image patches, and on each of them we plopped in an ellipse of a random size and a random orientation. And we gave the network the task of identifying what is the length of the major and semi-major axes of this ellipse, where we normalized those so that we weren't biasing in favor of the major axis. And here is the training history of the three different architectures that we tested this on. Orange is the conventional CNN. Blue is this rotationally invariant CNN. And red is an augmented CNN, where this is the classical CNN architecture, but the data has been augmented. So for every image, I have added to the training data set all 3 rotations of that image. So not only this image, but each rotation would be fed in separately as a new example to the neural network. So much larger data size, but a sort of way to try and get this rotational invariance without having to hard code it into the network. A note here on training times. So as we can see, the performance seems to go, this classical CNN does the worst, then we have the rotationally invariant CNN, and then the augmented CNN did the best. What this doesn't take into account is that the classical CNN ran very quickly. The augmented CNN took around 3.5 times as long to run as per training epoch as the conventional CNN, which makes sense because it's dealing with 4 times the data. And then the rotationally invariant CNN actually took the longest to run. This took around almost 5 times as long as the conventional CNN to run, because we're doing 4 convolution operations to every one in the conventional CNN. And because it's a custom architecture, it is not quite as optimized as the built-in TensorFlow operations. Okay, so one of the interesting thing here, though, is that the training and validation sets for this synthetic data set, we restricted the orientation of these ellipses to have a horizontal axis within about 30 degrees or pi/6 radians of the horizontal. So they're more or less horizontal with some variation, where the test set was allowed to include ellipses of any orientation. So the test set here is measuring how well these architectures are able to generalize from a training set that had sort of limited rotation to unrestricted rotation. And what we see here is that the conventional CNN really struggles with this. Final training and validation error are quite low, where the testing error here is huge. The scale on this first plot only goes up to 0.1, and the testing error is back to 0.7 here. So this is effectively untrained performance from the CNN. The augmented CNN and the rotationally invariant CNN, on the other hand, both do really well, and so are able to generalize from this restricted data set to the full rotation, which is what we would expect from being invariant to rotations, but it's really nice to see this play out in on data. One last thing to note on this synthetic data set is it's a good place to talk about approximate versus true invariance. So the rotationally invariant CNN has invariance hard-coded into it. We have built this architecture so that it will be truly invariant to rotation. So given these 2 samples, the bottom of which is a 90-degree rotation of the top image, so the major and minor axis lengths, the true ones are the same. The rotationally invariant CNN gives us the same outputs to a number of decimal places. Eventually there's minor variation because computers are not perfect. The augmented CNN, on the other hand, gives us pretty significant variation between its predictions on these rotations. In particular, on the minor axis length, on the top image, it is underestimating, and on the bottom image, it's overestimating the minor axis length. So we do actually have sort of real change here. And so this invariance is not, this is much more of a soft constraint that the augmented CNN has learned here. But that soft constraint does actually seem to be perhaps performing better numerically than the hard constraint from the rotationally invariant CNN. Okay, let's talk about some real-world data now. So this is an example of some of the input data that we're looking at. This is the output of, this is forecast data from the Ver Hoef forecasting algorithm that has been processed through Hagelschlag, which is an algorithm for detecting storms in that forecast data and computing certain attributes of those storms. Where one of those is the actual region of where the storm activity is taking place, which is what's outlined in gray here in the center of this image. And one of the other things that Hagelschlag does is takes an ellipse and finds the ellipse that best fits this gray storm area. And it outputs the major and semi-major axis lengths of that ellipse. And so for most of what we're going to talk about for the rest of this, those are our targets now, are those normalized major and semi-major axes of that sort of storm capturing ellipse, which are attributes that are closely tied to the storm mode, so is also not completely unrelated to that. Okay, so same three architectures, CNN, rotationally invariant CNN, and augmented CNN on these training data. This produced effectively the same story as the synthetic data set, just with a bit, with the results sort of tightening up a little bit, I would say. The conventional CNN still doesn't quite achieve the same level of accuracy in the same number of epochs, but is also running much faster in terms of wall clock time. And the rotationally invariant network and the augmented CNN are both performing slightly better overall, with the augmented CNN beating out the rotationally invariant network. We also wanted to do a similar test where we wanted to see if the rotationally invariant network and the augmented network would be able to generalize better than the conventional CNN. Now, in this case, sort of restricting on the orientation of the storm felt like a little bit of an unrealistic use case for this, and an unrealistic restriction and generalization. So for something a little bit more relevant, we used storm motion, using the Bunker's storm motion algorithm, which was, again, included in the input data from Hagelschlag. And the training and validation data, which is being displayed here, the performance over training, was restricted to storms that were eastward moving, where the test set was restricted to westward moving storms. So we wanted to see whether training on, in this data set, sort of the more common eastward moving storms would be, whether our algorithms would be able to generalize to the less common westward moving storms. And it's interesting to note here that doing this restriction did slightly reduce our training set size, and when we did that, it seems that the rotationally invariant network performed slightly better, which rotationally invariant, these rotationally invariant networks theoretically are able to have some performance benefits on smaller data sets, which may be why it was able to overtake the augmented CNN in this case. Okay, and now if we look at our, particularly the testing error here compared to the final training error and validation error, what we see is we don't get that same clear story that we had in the synthetic dataset case, where we had the CNN clearly struggling on to generalize from this restricted case to the more general one, and the augmented CNN and the rotationally invariant CNN doing way better. Here, all three algorithms seem to be able to generalize quite well to this new disjoint test set, where there's slight variation. The rotationally invariant error went down a little bit, the augmented CNN error went up a little bit, but these differences are so small that it's very hard to say that any of these are meaningfully better than the others on this task. Okay, and as a final question to look into here, we talked about in all of these architectures so far, we did a bunch of rotationally equivariant convolutions. And then at the very last possible step, we applied the rotationally invariant pooling, then flattened and moved on. But it's a valid question to ask, well, why did you wait so long? Why not move to rotational invariance earlier? And that's what this is somewhat busy graph is showing. So if we look at the gold lines here, these are the output of applying invariance after the very first layer. So you do an equivariant convolution operation and immediately move to invariance. And we get the worst performance here because moving to invariance that early, we lose a lot of information. We lose a lot of the ability to distinguish between, well, where in the image actually is this? Because some of that rotation information is important, and we don't want to sort of just hard code that out too early. And as we sort of move our invariance deeper into the network, where this red lines are after, now after 2 layers we move to invariance, and blue is after 3 layers. We get increasing performance, but that stops being true after a certain point. Having the invariance occur after the 4th or 5th layer, or maintaining full equivariance all the way through and never shifting to invariance, we end up at a very similar error rate. We've sort of, by that point, extracted all of the information that we needed from rotation, and so moving to invariance is sort of we're no longer losing as much. And so this is useful and would be good to know going forward, because by moving to moving this rotational invariance earlier, we're actually able to speed up the algorithms by using more efficient convolution operations after that rotational invariance. Okay, so things that we are currently working on and will be working on over the next few weeks and months. So the big one is, I think, uncertainty quantification. I've shown a lot of results so far that are like, well, this one is 0.005 better than this other algorithm. And I'm really curious to know which of those results are, in some sense, real. Because is it just this particular run on this particular data with this particular random seed that made this algorithm perform better? Or is there a genuine, consistent, reliable difference in between them? And so that's what uncertainty quantification is hopefully going to be able to give us, as well as seeing if these different algorithms are able to shift the balance of this uncertainty and error between how much is coming from the architecture of the model itself versus how much is coming from just the data, or how much or how little of it we have. I also want to look at explainable and interpretable AI methods to see if there are these different architectures are learning different things, are picking up on different attributes of the inputs, and see if there's one that is focusing on sort of more perhaps climatologically relevant information. And also want to look at how these algorithms compare on things like consistency over time, because we have storm tracks that occur at multiple forecast hours, and we want to see if there's a difference in how consistent these are at predicting properties of those storms. And as well as all of this was done on data from the Ver Hoef forecasting algorithm. I want to see how robust these architectures are to shifting from that to the her algorithm. Okay, I really want to thank NCAR and the Sizzle Visitor Program so much for hosting me, the whole AIML group for being wonderful, welcoming hosts, and everyone here, particularly DJ, John, Charlie, Da, Tasia, Kristen, have been wonderful. And I'd like to thank my advisors and committee member, Henry, Emily, and Emma, for being supports, as well as these NSF grants for making this work possible. So thank you very much, and I'd be happy to answer any questions, either in person or from Slido.
All right, thank you very much, Lander. Really good presentation. Please go ahead and submit your questions to the Slido, and we'll, as soon as they start popping up, we'll start reading them off. In the meantime, start a kind of more generic question. Sure. What were some of the biggest challenges you encountered implementing the RICNN, and do you have any pointers for people who might be interested in other kinds of adding these kinds of invariances to their models? Yeah,
in terms of implementing, I think for me the biggest hurdle, particularly early on, was wrapping my head around. Ironically, as someone who is studying mathematics, it was wrapping my head around the algebra of it, of the, if we go back to, like, this first step made a lot of sense to me. And then trying to figure out how this was implemented once once the input was not just an image, but was a signal on a group, because that's a much more sort of abstract way of thinking about things. That was where it became more challenging, and got it sorted out eventually, but it took a while of sitting down and reviewing my group actions and stuff like that. So, yeah, thank you.
Any popped up on your side?
Cool.
So what are your plans for the fall?
Writing and doing the stuff that I said on the future work slide, and ongoing work, as well as I'm starting in on a new project, trying to build an automated identifier detector for atmospheric gravity waves in the Ver's day-night band, and trying to use harmonic analysis tools and like wavelet analysis to detect the like periodic structure of those. So a whole different side of mathematics and such, but it's fun.
Cool. Yeah, we do have a question. It is from Charlie. Great talk. Is it feasible to do rotationally invariant convolutions on less than 90-degree segments?
Can you say the last bit one more time?
Sorry. Is it feasible to do rotationally invariant convolutions on less than 90-degree? I assume less than 90-degree rotations.
Yeah. Absolutely. It becomes a little bit more technical, I would say, and like you have to make more choices on how you do that approximation. So one of like there's the larger your input data is, really, the sort of easier that process is going to be of doing a less than 90-degree rotation, because you're taking what is sort of fundamentally a square grid and doing some sort of interpolation to move these values around. And if your overall grid is larger and your filters are larger, then that interpolation is easier. The other thing I'll say to that is I was really, one of the things I was surprised by was how much performance you could get out of just the 90-degree rotations, because particularly in like this synthetic data set, these ellipses were at all sorts of angles. They were not restricted to these 90-degree rotations, and yet by just adding the 90-degree rotations, we were able to build something that was far less sensitive to any angle of rotation. So yeah, I think that was sort of one of the initial surprises for me, was how well using just the 90-degree rotations did. But yeah, that's a good question.
We have another question from Seth McGinnis. What did you have to do to implement the RICNN in terms of code? For example, did you have to rewrite entire subsystems, overload a couple classes, or just change kernels? Did you import lots of fancy math libraries, etc.?
No fancy math libraries necessary. No, in terms of coding, this is essentially a custom layer in TensorFlow. So I just subclassed the layer class and wrote my own convolution step, effectively. I think it would probably be possible to overload convolution and just sort of define your custom convolution step, but for my purposes, it was cleaner to create a whole new layer because I wanted to, in this architecture, I actually stored these four slices of this feature activation that had sort of these four slices in it as a three-dimensional array that then, after we apply rotational invariance, collapses down to a two-dimensional array. And so having the custom layer made it easier to handle those dimension changes. But yeah, it was a good exercise for me in learning how to code up custom layers. But once it's coded up, it functions identically to the built-in layers. I'm able to save and load the models built with this just fine. So that's been pretty satisfying to get that working.
Are you planning to open source your code?
Yeah, definitely. I'll be at some point putting this out. I think technically it is available. It's somewhere on GitHub right now, but in not any sort of well-documented or published sense. So there should be an open source version coming this fall sometime. Coming soon to computers near you.
All right, with that, I think, we go thanks from Seth. And with that, I think we'll wrap up. Let's thank Lander one more time.
Thank you.
And he'll be around as a visitor for one more day. But if you want to get in touch with him, feel free to email him. Can you flash your email address up on the screen again?
I don't know if I have it in the presentation. Yeah, it's probably the reliable way is I'm going to say reach out to me on Slack or let's see, I can probably just...
I can put it in the Slido as well.
Yeah, if you can put it in the Slido. Here, well, oh, I can't edit.
What's the...
It's my first name, Lander, L-A-N-D-E-R, dot V-E-R underscore H-O-E-F at colostate.edu. Cool.
Yep. Tasia just posted Lander's email on the Slido if you want to reach out to him and have any more questions. And he lives in Thornton, so I'm sure he'll be happy to come back to NCAR at any point in the near future to talk further. And he should also be at the AMS annual meeting, which if you have not submitted your abstracts, they are due tomorrow. So encourage everyone watching to submit. So thank you very much, everyone, and we'll tune in again next time for another exciting Sizzle seminar.